During World War II, the National Advisory Committee for Aeronautics, or NACA, focused its primary efforts on gathering data to improve the performance of production combat aircraft. However, when Germany fielded its first jet fighters, everything changed. It was now absolutely clear that the immense thrust generated by turbojet and rocket engines was the most direct path to total air supremacy. With fighter speeds steadily climbing, it was obvious that sooner or later, aviation would have to break the sound barrier. The committee's scientists knew one thing for certain. Before tackling the development of high-speed, let alone supersonic combat aircraft, they desperately needed new aerodynamic data. They had to find the simplest, cheapest, and fastest way possible to break through the sound barrier. The stakes could not have been higher. Whoever built the right scientific foundation first would gain an undeniable advantage, one that would make their combat aircraft practically invulnerable. At the time, knowledge about how airflow behaves at near-sonic speeds was razor-thin. All early attempts to build any kind of theoretical foundation ended in total failure. Practical experiments were the only way forward. But there was a problem. Standard wind tunnels would simply choke and stop working correctly the moment the airflow approached Mach 1. To move forward and keep researching, scientists desperately needed entirely new technical solutions. And those solutions were eventually found. Researchers started using a few unconventional approaches. First, they built specially equipped drop models. They released them from high altitudes out of a B-29 Superfortress. Second, they used compact models mounted directly onto the wing of a P-51 Mustang. In a dive, the aircraft could reach Mach 0.75. This gave them exactly the kind of data they needed. Third, scientists started launching special rocket-powered models right off the ground. These boosters would push the test vehicles to Mach 1.4. After this, the models would simply splash down in the Atlantic Ocean. Thanks to the rapid development of radar and telemetry technologies, those rocket-powered models turned out to be an absolute goldmine for the scientists. Ground stations could easily track the flight of these vehicles, recording their exact flight profiles. Meanwhile, onboard equipment filled in the rest of the picture. It transmitted detailed data on acceleration, angular rates, G-forces, and countless other critical parameters. However, this method had one major flaw. Most of these test models had an extremely limited lifespan, so more often than not, they were strictly single-use. In 1943, a bold new idea emerged. Scientists proposed researching transonic speeds using specially designed manned research aircraft. The concept was to install the most powerful rocket engine available into a custom airframe. It would also carry all the necessary telemetry and recording equipment. But then something completely unexpected happened. The pilots flat out refused to fly it. When NACA Chief Test Pilot Melvin Goff heard about these plans, he bluntly stated, "No NACA pilot is going to get into an airplane with that damn firecracker." Still, the need to push aerodynamics forward could not be ignored. Eventually, they managed to convince the pilots to get on board. They explained that the risks involved with these test flights could be kept to an absolute minimum. To ensure this, the flights would take place at extremely high altitudes and strictly in level flight. Under these conditions, aerodynamic loads on the airframe and physical stress on the pilot would remain minimal. On top of that, if any unexpected issues arose, the pilot could react instantly. They could simply pull back the throttle to reduce airspeed. Behind closed doors at the National Advisory Committee for Aeronautics, or NACA, the idea of building a high-speed research aircraft gradually evolved into a top-secret program. It was given the code name MX-524. Its ultimate goal was something that just yesterday seemed like pure science fiction. The goal was breaking the sound barrier. In mid-December 1943, a major conference brought together representatives from NACA, the Army Air Forces, and the Navy. To streamline the ambitious MX-524 program, the Army Air Forces agreed to foot the entire bill for the project, and Bell officially landed the contract to build the experimental aircraft, designated the X-1. Over at Bell, the development of their experimental aircraft was spearheaded by Robert Stanley. He was not just a standout Caltech graduate and a brilliant aerodynamicist. He was also a renowned test pilot who had previously flown the experimental XP-59 jet. Even though the project was completely unprecedented and technically complex, development progressed at a remarkable pace. The biggest headache for the engineers was figuring out the right shape for the wing and the horizontal tail. Following John Stack's advice, the designers used a clever trick. They made the wing and the horizontal stabilizer different thicknesses. The stabilizer ended up slightly thinner than the wing, 8% thick versus 10%. That difference was absolutely critical. It ensured that different parts of the airplane did not hit their critical Mach number all at the exact same time, which guaranteed the pilot would not lose control at those extreme speeds. When it came to the actual shape of the wing, the team at Bell decided to play it safe. Instead of fitting the X-1 with a swept wing, which was still largely unproven at the time, they went with a more conservative approach. They chose a tried-and-true straight wing design. To make the horizontal stabilizer even more effective, John Stack pushed for an innovation. Bell designed the system so the pilot could adjust its angle of incidence right in mid-flight. At relatively low speeds, the pilot controlled the aircraft using standard elevators. But as the airplane accelerated, the pilot could pivot the entire stabilizer. This maintained perfect pitch control. The fuselage of the airplane itself was shaped like a .50 caliber bullet. This choice was no accident. Ballistics experts had long known that this exact shape ensures the most stable flight at supersonic speeds. On March 16, 1945, the Army Air Forces ordered the company to build yet another, now the third, prototype of this experimental aircraft. In the fall of that same year, the company successfully finished assembling the airframe of the first aircraft. However, the highly anticipated start of the flight tests had to be pushed back time and time again. The reason was simple. They did not have a working engine. Reaction Motors was in charge of developing the rocket engine, but their engineers were falling disastrously behind schedule. Their main stumbling block was the fuel turbopump, a deceptively complex piece of hardware. After many failed attempts, the Reaction Motors engineers decided to just ditch this component altogether. Instead, they went with a simpler pressure-fed system. Now the fuel flowed into the combustion chamber straight from the tanks, forced out under pressure by compressed nitrogen. Not wanting to waste any precious time, the engineers at Bell came up with a pretty bold idea. They decided to get the X-1 airborne completely without an engine. To do this, they planned to use a B-29 Superfortress. It would carry the experimental aircraft up to high altitude and drop it into free flight. This approach would let them test the aerodynamics and handling characteristics of the airplane before Reaction Motors finally delivered the engine. The Army Air Forces signed off on the idea. They handed over a standard production B-29 bomber to the NACA research agency. They stripped it of all its weapons and extra equipment. Then they completely rebuilt the bomb bay. After such extensive modifications, this bomber received a new designation. It was called the EB-29. During the conversion of the carrier aircraft, the biggest headache for the engineers was figuring out how to get the pilot into the cockpit of the experimental X-1. The thing was, the X-1 was originally designed to take off normally from a runway. This meant the pilot was supposed to enter the cockpit through a small side door. But now, the rocket plane was tucked high up inside the bomb bay of a larger mothership. Because of this, getting in the normal way just was not possible. The engineers had to get creative and rig up a special elevator. Here is how it worked. The X-1 pilot, wearing a bulky, high-altitude pressure suit, would step onto a small, enclosed platform. Then, using winches, the platform was carefully lowered down to the door of the X-1. The pilot would climb into the cockpit and seal the door behind him. After that, the empty platform would be hoisted right back up into the bomb bay of the carrier plane. For the first unpowered glide flights, they picked a remote, unpopulated area in central Florida. Jack Woolhams was assigned as the chief test pilot for the project. The flight profile itself followed a pretty straightforward, well-worn routine. The carrier plane would climb to around 30,000 feet, then release the experimental X-1 into freefall. After the drop, Jack Woolhams would glide back down toward the airfield. He would run through specific mid-air maneuvers. This was to thoroughly test the aircraft handling, but they ran into an issue. Because of its relatively high wing loading, the X-1 came in hot. A standard runway barely gave it enough room to land safely. This tricky characteristic forced the team to move the rest of the flight testing. They relocated out to Muroc Army Airfield. We now know this as Edwards Air Force Base. Out there, the pilots had a massive, perfectly flat, dry lake bed completely at their disposal. This gave them practically endless runway. The final glide flights took place at this new location. In March 1946, this forced but necessary phase of the X-1 testing wrapped up successfully. All in all, the team logged 10 glide flights. Then came preparations for the main event. This was the powered flight using the liquid propellant rocket engine. In early October 1946, the second XS-1 airframe arrived at Mach. It was powered by the XLR-11 rocket engine. It burned a mix of liquid oxygen and ethyl alcohol. Built by reaction motors, this engine produced about 6,000 pounds of thrust. The thrust was spread across 4 independent combustion chambers. The pilot could ignite or shut them down mid-flight. He could do this in whatever combination he needed. Meanwhile, the first aircraft was sent back to Bell. They needed to have the exact same power plant installed. A large team of engineers and scientists from NACA arrived on base. They were there to manage the complex test program. Just before the powered flights kicked off, a new test pilot was assigned to the project. His name was Chalmers Hubert Goodland. He replaced Jack Willems. Willems had tragically died flight testing a modified P-39 Airacobra fighter for air racing. With a new pilot in the seat, the official acceptance trials for the aircraft finally got underway. Bell, the manufacturer of the aircraft, suggested a simplified flight test profile. They proposed to take off, climb, and accelerate to Mach 0.8. Then the pilot would enter a steep dive and pull out at 8 Gs. They figured the stability and handling of the XS-1 were already proven. This was because the experimental aircraft had successfully completed its unpowered glide flights. But the NACA scientists were not on board with this approach. They needed a proven, reliable aircraft for serious research. They insisted on conducting a series of flights at lower speeds first. This would let them evaluate the handling of the aircraft under power. They only planned to push past Mach 0.8 during the final phase of testing. To get a detailed look at its handling, performance, and stability, the pilot had to perform a full set of standard flight test maneuvers. These included climbing spirals and rolls around all 3 axes. The pilot also had to execute slow rolls, controlled side slips, rolling pullouts, and 0G climbs. Only after successfully passing these rigorous tests would NACA officially accept the aircraft, and only then would Bell get paid. Ultimately, this thorough approach was deemed necessary. The main flight test program officially kicked off. The historic first rocket-powered flight took place on December 9, 1946. The aircraft successfully took off from the perfectly flat Muroc dry lake bed after a conventional ground takeoff roll. After just a month of intensive flight testing, Chalmers Hubert Goodland reached Mach 0.8 in the XS-1. He then climbed to an altitude of 35,000 feet. In March, the first prototype joined the test program as well. It made its first powered flight on April 10, 1947. Overall, during these acceptance trials, the 2 experimental aircraft completed 21 flights. On June 30, 1947, representatives from the United States Air Force and NACA met. They agreed to split the test program into 2 independent paths. Each organization got its own XS-1. NACA continued using their aircraft for conventional ground takeoffs to study transonic speeds. The military, on the other hand, took a different approach. They opted for an air launch, dropping their XS-1 from a massive B-29 mothership. Their main goal was to break the sound barrier. The air launch saved a significant amount of fuel. This was because the pilot did not have to burn it during a heavy takeoff and climb. Naturally, starting at altitude with full tanks allowed the aircraft to reach much higher speeds. To execute their part of the program, NACA opened a new flight test unit at Muroc Air Base on September 7, 1947. Walt Williams was put in charge of operations. Meanwhile, test pilots Herbert Henry Hoover and Howard Clifton, Lilly, took the controls of the experimental aircraft. Meanwhile, the Air Force took delivery of their XS-1 from Bell in August 1947. They wasted no time starting their flight program. They appointed a young 22-year-old Captain Charles Elwood Yeager as the lead test pilot for the military. He had only recently joined the Elite Flight Test Division at Muroc, yet he was already something of a legend. Yeager was an outstanding World War II fighter ace, credited with 13 aerial victories. On top of that, he had achieved ace in a day status. He did this by shooting down 5 enemy aircraft in a single mission. Every flight day for the X-1 program began with a meticulous inspection. The fuselage of the aircraft had very few access panels, making it an absolute nightmare for mechanics to ensure the fuel lines had no leaks. Fueling the rocket plane was another incredibly dangerous step. Mechanics had to carefully purge the system with nitrogen before pumping in the highly volatile alcohol and liquid oxygen. Because the liquid oxygen boiled off so quickly, engineers even installed a top-off tank inside the bomber to continuously replenish the attached X-1 throughout the long climb to altitude. During the heavy takeoff and the long climb to altitude, the test pilot stayed up in the warm, pressurized crew cabin of the B-29. Once the aircraft reached 10,000 feet, the pilot made his way back into the freezing, unpressurized bomb bay. From there, he used a small makeshift elevator. He lowered himself down to the cramped cockpit of the X-1 and carefully climbed inside. As soon as the pilot was strapped in and the hatch was sealed, the bomber crew disconnected the liquid oxygen top offline. This prepared the rocket plane for the drop. At an altitude of around 25,000 feet, the pilot of the X-1 rocket plane turned on the electrical power. He then started prepping for the drop from the B-29 mothership. This was scheduled for just over 29,500 feet. Reaching the target altitude, the pilot began pressurizing the propellant tanks with nitrogen. About 30 seconds to a minute before the drop, they ran a purge on the oxidizer feed system. The drop countdown was called by the co-pilot of the B-29 bomber. The moment the shackles released, the X-1 dropped away in freefall. Once clear of the bomber by a safe distance, the pilot ignited the first combustion chamber, followed by the others. Throughout the powered flight, the pilot had to closely monitor the gauges. He maintained the fuel tank pressure about 10 to 16 pounds per square inch higher than the oxygen tank. This pressure differential forced the mixture to run slightly rich. It ensured a stable burn and prevented a mid-air flameout. The historic moment came on August 29, 1947. Famed test pilot Chuck Yeager took the controls of the X-1 for his very first flight. Interestingly, for his first 3 drops, Yeager did not even ignite the engine. They were strictly unpowered glide tests. Power testing only kicked off on his 4th flight. At full throttle, the engine had a very short burn time of just about 3.5 minutes. To capture the instrument readings, a film camera was mounted over the pilot's shoulder, continuously recording the panel. At the same time, data on pressure, G-loads, and control inputs was telemetered straight back to the ground. In total, the aircraft was packed with about 990 pounds of test instrumentation. This allowed the team to gather highly precise data. During this flight, he pushed the speed to Mach 0.87 at an altitude of around 39,000 feet. But things got rough on the 5th flight. As the speed reached Mach 0.89, the aircraft experienced severe buffeting and sudden uncommanded rolling. On the 6th flight, they bumped the speed up to Mach 0.91. But the real test of nerves came on flight number 7. During a routine maneuver, the elevator completely lost effectiveness and stopped responding. What saved the aircraft was a trimmable horizontal stabilizer, which had been installed at the insistence of engineer John Stack. By adjusting the pitch of the entire stabilizer, Yeager managed to pull a 2G maneuver and safely fly the aircraft back to base. Once safely on the ground, the engineers figured out exactly what had happened. It turned out that as the aircraft approached the speed of sound, a powerful shockwave moved aft along the tail. This blanked out the elevator and rendered it useless. This incident led researchers to a crucial conclusion. For an aircraft to safely transition through the sound barrier, an all-flying tail is absolutely essential for reliable pitch control. The real reason these flights did not end in disaster was a unique testing method developed by the NACA Research Center. They called it the STEP method. The whole idea was to proceed very cautiously, incrementally expanding the flight envelope. If telemetry showed or the pilot reported that the aircraft was exhibiting adverse handling characteristics, they would immediately back off that specific test point. This allowed them to land safely and analyze the data. Then came the morning of October 14, 1947. The flight plan called for Chuck Yeager to take the next step and push the aircraft to Mach 0.97. During the pre-flight briefing, NACA engineers strongly advised him not to push past that limit, but Yeager had already secretly decided he was going to push it even faster. To be honest, he was flying through some serious pain that day. He had cracked 2 ribs falling off a horse the night before. At exactly 10 a.m., the heavily modified B-29 mothership lifted off the runway. About 20 minutes into the flight, climbing through 5,000 feet, Yeager lowered himself through the bomb bay. He squeezed into the cramped cockpit of the experimental X-1 rocket plane. Passing 20,000 feet, ground control radioed in. Radar tracking had acquired the aircraft. They were cleared to begin the drop sequence. At 10:26, the X-1 dropped from the belly of the B-29. Yeager immediately ignited all 4 chambers of the liquid propellant rocket engine. The aircraft surged forward. Passing 35,000 feet, he shut down 2 of the chambers to dial back the acceleration as he neared the top of his climb. From there, he leveled off at 42,000 feet. The needle on the Mach meter kept steadily creeping up. 0.83, 0.84, 0.88, 0.92. Suddenly, the airframe began to buffet heavily. This buffeting was caused by turbulent shockwaves rolling off the wings and slamming into the tail. It caused the right wing to drop slightly. To maintain control, Yeager adjusted the trimmable horizontal stabilizer. He used aileron input to level the aircraft out. Once stabilized, he trimmed the nose down slightly and ignited the 3rd chamber. The Mach meter crept to 0.98. Then the needle suddenly jumped right off the scale, passing that magic number of Mach 1. Down on the ground, observers heard a massive sonic boom echoing across the desert. It sounded just like a distant explosion. It meant only one thing: an aircraft had successfully broken the sound barrier. Yeager calmly got on the radio. He reported that the X-1 was responding perfectly to control inputs, with all flight systems operating normally. With the milestone secured, he cut the engine and began a smooth glide back down. Descending through 33,000 feet, the X-1 decelerated back below Mach 0.7. Soon after, the ground crew confirmed the initial telemetry. The sound barrier was officially a thing of the past. Flight data showed that the top speed during this historic run had hit Mach 1.06. It didn't take long for word of Chuck Yeager's historic flight to spread around the airbase. However, people only talked about it in hushed tones, since the flight test program was highly classified. While Yeager celebrated his success, the test program still had hurdles to overcome. The day after the historic flight, the 2nd prototype of the X-1 suffered a serious mishap. NACA test pilot Herbert Hoover was flying a routine unpowered glide flight without even igniting the rocket motor. However, on his landing approach, he slightly misjudged his airspeed and altitude. As a result, the aircraft bounced hard on the dirt runway a few times. The impact was so severe that the nose gear simply could not handle the stress and collapsed. The X-1 research aircraft dropped its nose into the dirt. It skidded along the lake bed for over 330 feet. Naturally, after a major mishap like that, the damaged aircraft had to be sent back to the factory for extensive repairs. This grounded it from October all the way until December 1947. Because of this frustrating delay, the civilian NACA pilots fell significantly behind their Air Force counterparts. It was not until December 16, 1947, that Herbert Hoover finally made his first powered flight. On this flight, he reached Mach 0.7. He would not go on to break the highly sought-after sound barrier until March 10, 1948. Even so, he made history, becoming the first civilian pilot to go supersonic. In 1948, the military updated its aircraft designation system and program names. From that point on, the legendary record-setting aircraft was given its final and much more famous name. It was called the X-1. On May 2, 1949, Charles Yeager thrilled the public once again with another impressive record. This time, he pushed the aircraft to Mach 1.45. Shortly after, on August 8th of that same year, another talented Air Force test pilot, Major Frank Kendall Everest, set an absolute altitude record. He climbed to a staggering 71,900 feet. This was a major milestone. It marked the 125th flight of the test program. However, pushing the limits of speed and altitude did not come without risks. On August 25, 1949, during a routine test flight, Frank Kendall Everest found himself in a life-threatening situation. At an extreme altitude of around 68,900 feet, One of the glass panels of the canopy suddenly cracked. The cockpit instantly depressurized. The high-altitude pressure suit of the pilot immediately ballooned up from the sudden drop in cabin pressure. It took nerves of steel, sharp professionalism, and sheer courage for Everest to save the day. He managed to get himself out alive and bring the aircraft back with him. This terrifying incident served as a major wake-up call for the engineering team. Shortly after, they developed an entirely new, much safer, and far more reliable pressure suit called the T-1. All this tremendous effort didn't go unnoticed. In 1947, the National Aeronautic Association awarded the team of designers and test pilots the prestigious Robert J. Collier Trophy. The Collier Trophy is awarded annually for the greatest achievement in American aviation. President Harry Truman personally presented the award to the honorees. At the official ceremony held at the White House, he read the names of the recipients. Among them was John Stack, a prominent scientist and head of transonic flight research. Also recognized was Lawrence D. Bell, president of the Bell Aircraft Corporation, for the bold design and construction of the X-1 research aircraft. And of course, there was Air Force Captain Charles Yeager for piloting the first manned flight in history to break the sound barrier. Over time, the very first airframe of the legendary X-1 reached the end of its service life. In total, it completed 83 test flights. It was this exact aircraft that achieved a top speed of Mach 1.45. It also climbed to a maximum altitude of 71,900 feet. The aircraft's service history was remarkable. It suffered multiple in-flight fires, lost cabin pressurization, and even had structural components tear off in mid-air. Despite all this, the airplane survived and fully accomplished its mission. All the invaluable scientific data gathered during these tests was immediately shared with leading aerospace manufacturers for further study. The aircraft made its final flight in 1949. Carrying only half its maximum fuel capacity, the X-1 managed to take off from the ground entirely under its own power. It required a takeoff roll of just 2,300 feet. It lifted off at roughly 163 miles per hour. During this flight, the airplane demonstrated an absolutely phenomenal rate of climb. Just 100 seconds after liftoff, it had already reached an altitude of 24,900 feet. After this spectacular grand finale, the famous aircraft was officially handed over to the Smithsonian Institution. It remains proudly on display there to this very day. The third X-1 airframe, however, turned into a massively drawn-out engineering project. Bell wasn't able to hand it over to the test pilots until 1951. Its main technical feature was a new turbopump fuel system. This innovation allowed the rocket plane to stay in the air significantly longer than its predecessors. These powerful pumps ran on highly concentrated hydrogen peroxide. This liquid violently decomposed as it passed over a special catalyst. Inside the new aircraft, engineers managed to fit about 600 gallons of liquid oxygen and roughly 660 gallons of a water-alcohol mixture. With this increased capacity, the continuous burn time of the rocket engine jumped to 4.5 minutes. Engineers specifically chose a 5-to-1 alcohol-to-water mixture. This was because it produced a much higher specific impulse than the pure alcohol used in earlier models. The aircraft made its first unpowered glide flight on July 20, 1951. At the controls that day was civilian test pilot Joseph Cannon. The second flight was scheduled for November 9th. This was when they planned to ignite the rocket engine for the first time, but it never happened. While the third X-1 was being topped off with liquid oxygen, a fire suddenly broke out. It exploded on the tarmac, destroying both the rocket plane and its carrier aircraft. The test program, however, definitely didn't end on that tragic note. Back in the fall of 1947, the Air Force had already ordered upgraded versions from Bell, designated the X-1A, X-1B, and X-1D. These new airframes featured raised bubble canopies for better visibility and stretched fuselages to accommodate much larger fuel tanks. Naturally, these upgrades made the aircraft significantly heavier. This meant a modified carrier aircraft had to be developed based on the more powerful B-50A bomber. Each variant had its own specific mission. The X-1D featured a cutting-edge fuel system, but its story was cut short. On August 22, 1951, during its very first flight attempt, a nitrogen leak caused an onboard explosion. The rocket plane was engulfed in flames. This forced the commander of the B-50A mothership to emergency jettison it mid-air to save the crew. In January 1953, the next model, the X-1A, arrived at Edwards Air Force Base. It had an ambitious goal: to hit Mach 2, twice the speed of sound. The flight testing was handed over to legendary test pilot Chuck Yeager. The first 3 flights went strictly by the book. Step by step, Yeager pushed the envelope. He first reached Mach 1.3 at an altitude of nearly 45,000 feet. Then he pushed it to Mach 1.5 at 60,000 feet. Finally, he hit Mach 1.9 at that same altitude. The real drama unfolded during the 4th flight on December 12, 1953. After dropping from the mothership, Yeager ignited the engine and rapidly climbed to 60,000 feet. By the time he leveled off for horizontal flight, his speed was already pushing Mach 1.4. Climbing even higher to 70,200 feet, the aircraft flew level at Mach 1.9. It was accelerating by a staggering 31 miles per hour every single second. The flight peaked at a staggering altitude of 76,100 feet. Here, the X-1A hit Mach 2.51. To put that in perspective, the true airspeed of the aircraft was an incredible 1,650 miles per hour. This was even though the indicated airspeed in the cockpit was only showing about 440 miles per hour. This massive discrepancy is due to the extremely thin air at those high altitudes. Up to this point, the aircraft had handled surprisingly well, but right at engine burnout, the aircraft instantly departed controlled flight. It began tumbling violently out of the sky. The brutal G-forces knocked Chuck Yeager unconscious. In just 51 seconds of uncontrolled descent, he plummeted down to 24,600 feet. As his airspeed bled off to 168 miles per hour, the aircraft pitched up violently. It was right on the edge of snapping into a deadly inverted spin, pulling a punishing 11 Gs in the process. At that critical moment, Yeager miraculously regained consciousness. Relying on his vast experience, he managed to recover the aircraft from the spin and bring it in for a safe landing. Later on, this very same X-1A set a world altitude record for the time, reaching over 90,400 feet. Once the Air Force wrapped up its test objectives, the X-1A was handed over to researchers at NACA. Unfortunately, the aircraft met a tragic end. On August 8, 1955, just 17 seconds before its scheduled drop from the carrier aircraft, a low-order explosion went off inside the experimental plane. The fuel system had ruptured. Luckily, the pilot reacted instantly. He scrambled out of the cockpit of the X-1A and climbed back up into the safety of the B-50 mothership. The bomber itself was not severely damaged by the blast. However, safety protocols strictly forbade landing with a fueled, damaged rocket plane attached to the belly. So the aircraft commander had no choice but to jettison the X-1A and let it crash. Other models continued the vital research. The X-1B became an outstanding flying testbed, logging 27 flights to test innovative reaction control systems before being permanently grounded in 1959 due to fatigue cracks in its fuel tanks. To keep pushing the boundaries, engineers completely overhauled one of the original airframes. Redesignated as the X-1E, it was fitted with a thinner wing profile, a new turbopump system, and for the first time in the program, an ejection seat. In October 1957, legendary NACA test pilot Joe Walker pushed the X-1E to Mach 2.24. The engineers even planned to modify it to reach Mach 3, but dangerous fatigue cracks forced its retirement in 1958. Looking back, it's safe to say that the early rocket-powered experimental aircraft of the X-1 series were some of the most important research tools of their era. These daring flights gave engineers a deep technical understanding of how aircraft behave at extremely high speeds. The massive amount of data gathered during the program led to dramatic improvements in military aircraft performance. Engineers were so effective at applying this knowledge to new designs that NACA decided to keep the momentum going. They wanted to push the research even further. That is how an entire family of unique aircraft was born. They went down in history as the famous X-planes. Meanwhile, the modest NACA flight test station at Muroc transformed into a massive, cutting-edge flight research center. Today, virtually every American military aircraft is tested there before entering service. Fortunately, the surviving X-1 experimental aircraft have been carefully preserved for future generations. The legendary XS-1, flown by the renowned pilot Chuck Yeager, now hangs majestically at the Smithsonian's National Air and Space Museum. The X-1B found its home at the National Museum of the United States Air Force at Wright-Patterson. And our spotlight aircraft, the veteran X-1E, is proudly displayed on a pedestal. It sits right in front of the NASA Flight Research Center at Edwards Air Force Base.